Hey everyone, today I'm going to be solving 1650 on LeetCode called lowest common ancestor of a binary tree. So this is the third part of the question's lowest common ancestor. As the name implies, there's number one, there's number two, maybe there's even number four and number five, but this is number three. I've already probably done number one and number two. Number one is just finding the lowest common ancestor of a binary tree, and you're pretty much given just a binary tree. So every node, there's like you're given a root node, and each node has a left and right child. But the one thing that changed here is, put myself over there, is that you're also given the parent node, and I'll show how you could actually, like, if you've done lowest common ancestor of binary tree number one. If you haven't, go and do it and then come to this question. You'll see that that one takes about O of n space and O of n time, where O of n is, or n is like the number of nodes in the tree. So this one, you could actually, instead of just taking O of n time and O of n space, you could actually do it in O of 1 space and O of n plus O of m time, I think. But yeah, the big optimization is the space complexity optimization. And I'll show exactly how to do that. But first, let's get into, if you haven't done any of these questions, like what exactly is what is the lowest common ancestor? Let's see. Where's my pen? I have an Epic pen. Where'd this go? So it's taking a second to load. Oh, there you go. I'm going to be using this Epic pen. So what exactly is the lowest common ancestor of a binary tree? Let me get my... So what is it? Like, it's pretty much what the name implies. Like, an ancestor is... Like, pretend I have two nodes. I have a node like 6 and a node 2. Who's the lowest common ancestor? 5 is an ancestor. 3 is an ancestor. So the lowest common ancestor would be 5, because this is the ancestor that's common to both 6 and 2. And it's like the lowest, like it's the closest one to them. You don't care about the, like, who cares about the great grandparent that we're all related to? But yeah, like our closest ancestor is our grandparents, for example. So we'll do another quiz. Like, pretend I have 4 and 6. Who's the lowest common ancestor? 5 again. Is it 3? No. What about 7 and 8? Okay, finally it's 3, because that's the first common ancestor that they have. So our goal is to figure out who the lowest common ancestor is in O of n time, or O of n plus m time, and O of 1 space. And we do that because we have pointers. Like, we're given a p and q. Pretend we're given p here and a q here. And we also have every node actually has a pointer to their parent. Right? So that, it essentially makes it like we're traversing two linked lists, and it essentially boils down to this question over here of the intersection of two linked lists. Because like I mentioned, pretend since we all have they all have parent nodes, they essentially become linked lists. So if we can solve the intersection of two linked lists, we could also solve that lowest common ancestor question as well. Cool. Take a deep breath. Let's get this done. So how do we find the intersection of two linked lists? I'm basically just going to show you exactly how to do it and the intuition behind it, and then explain the intuition behind it. So we pretty much, if we're trying to find so what's the intersection of two linked lists? Here, it's C1. What about here? It's 8, because that's where the two linked lists intersect. What about here? It's 2, because that's where they intersect. So if we can find the first point of intersection, So for example, if we have nodes 6 and, let me just reiterate this again. Imagine like this is P and this is Q. Like the first time that these nodes like pretend we're looking them at as linked lists, the first time that they intersect is the lowest common ancestor. So if we could find when these two linked lists intersect, we can find the lowest common ancestor. Cool. Let's get back into it. Let me revert that. So how do we do that? We essentially have 3 cases here. Pretend that they don't, like the first case is they don't intersect. It's essentially what the trick to this is, and I'll explain mathematically why it works and the intuition why it works after, is that we do a 2-pointer technique. You keep 1 pointer on one node and 1 pointer on the other node. So pretend we have 2 heads here because we're given 2 linked lists. You started at the head of both linked lists, and then the first case is they don't intersect, right? You pretty much like move them. You move them up like one at a time. Like you basically just like move them forward until they meet, and if one reaches the end of the linked list, you move it to the head of like the other one. I'll show how that works. So yeah, it probably works better if we show like the more complicated case first, and then slowly move down. Let me think about it. Yeah. So essentially how this works is you in one iteration, you start each pointer at the head of like the respective linked list, and then you move them up by 1 node for every iteration. So from iteration 1, we move it up. Second iteration, we move them both up again, right? Third iteration, we move them up. Fourth iteration, we're just like for every iteration, you're moving the pointer up by 1 node on each linked list. Once one reaches the end, you move it to the head of like the other linked list. Now you go here, right? And now you move it again. This is the iteration 6. And then you just keep moving them forward 1 node at a time until at some point they converge at one specific node. That's kind of the trick to the question. I'll show why that kind of makes sense, like why that actually makes sense, and what's the like mathematical reason that makes sense. Pretend we have 2 linked lists that are exact same length, and we both start them at the same, like if we point the pointer at the same node or at the head of both linked lists, then we just move them forward. For each iteration, we move one forward, right? Since they both started the same distance away from the intersection, if we move them up by 1 at each point, they'll eventually meet at the intersection at the exact same time, right? So that's when that's the case if the 2 linked lists intersect at the same exact point, right? Or at the same number of nodes. So if the intersection is both the 3rd node for each linked list, right? Sorry. Okay, but then look at this case, right? The intersection is the 4th node here and the 3rd node here, right? So essentially why we just move them across the linked list and then point the other pointer at the head of the other linked list is because our goal is to like equalize them, get them the same distance away from the intersection. So see how this works. Pretend we move 1 node up here, right? Then we move another, and then we're moving 1 at a time, right? 1 at a time. Then we move this one to the front here. After 6 iterations, or Sorry, I did that too fast. Let me do it again. Iteration 1, iteration 2, iteration 3, iteration 4. Then move one up here, because like you're moving it to the head of the other one. Then iteration 4. Then you finally go to iteration 5. And now since that one got to the end, you point it to the other one. And now you have two. Now you could see that they're both the same distance away from the intersection as the other one. Or they're both the same distance away from the intersection. So then it pretty much boils down to this case. Now when you just move them forward, they just meet in the middle. So that's how it works for the case when the intersection are different, or the number of nodes before the intersection are different between the nodes. If it's the same, it will just they'll just converge faster. And if they never have an intersection, they'll just never converge. Put that. And yeah, you'll see like they'll never converge. And then you could just return false. So that's kind of how you solve the intersection of two linked lists. It's not that intuitive, but this is GPT's explanation, which I think was pretty good. It's like the two-pointer technique to find the intersection of two linked lists isn't immediately intuitive. Let's deep dive into it. So two linked lists with different lengths may intersect at some point. If we naively traverse both lists from their respective heads, we can't directly compare nodes because their lengths are unequal. So we're not really we won't converge at the same time, right? So, but if their lengths are the same, we'll end up converging at the right time. So to solve this, the two-pointer technique aligns the lengths effectively by swapping the pointers after one full traversal of each respective list. Sorry, I can't speak. Why it works. If you wanna know why it works, just ask GPT. The math is there. But the intuition, you probably have to think about it for a while, but the intuition is essentially you just trying to make them the same distance away from the intersection. And then, and then that allows them to eventually converge. Let me implement that to solve this 160, and then implement that same logic to solve 1650 here. So what did we say? We have head A and we have head B. Pretty much once we get to the end of one node, we want to point it back to the head of another node. So we say return false. We'll say head. We'll say top. And then let's carry a variable for if we did a switch already. Sorry, head A. Switch top. Then we'll also have bottom. And then we'll switch the bottom. And then we'll do head B. So while top is not equal to bottom. So I'm not really covering for the case that they don't have intersection. I'll write that down. I'm sort of assuming that they do have a intersection. So while top is not equal to bottom, we keep this running. So let's see. While top is not equal to bottom. Okay. Let's do this. While top is not equal to bottom, we're going to have our pointers so now we have one pointer at the first linked list, one pointer at the other. And what we're going to do is we're going to do top dot next equals, or top equals top dot next. That's how we move the pointer upwards. And then we're going to do bottom equals bottom dot next, right? Bottom equals bottom dot next. And we say if top dot next is none, that means it's at the end, and switch top is false. What I'm going to do is I'm going to put top, if the top dot next is none, and I'll do top equals the bottom, essentially. So I'll point it to this one, and I'll do switch top equals to true. And I'll kind of do that for the bottom one as well. Top, if bottom dot next is none, and switch bottom is false, switch bottom is here, I'll do bottom, and I'll switch it to head A. So now they should eventually meet. Yeah, because I'm literally just doing the logic where I'm moving them forward. Let's see, while top. Okay. Let me see. If I move them forward. Okay. If top equals so I'll say if top equals bottom return top. See if that works. Because eventually they'll converge. Wow. Okay, wait. I just need to debug this edge case. So it got none type, no attribute next. So eventually got here. While top the next is. Let's do just case 1 first. That worked. Okay, see, I'm not grabbing the other case. While top dot next here. Bool object has no attribute. Where did this fail? Line 79. This is not the best way to debug, by the way. I literally just ran the code. Use test case. I shouldn't be doing that. Showing y'all bad examples. Okay, we have list 1563. Skip A. Where is that? Okay, let me figure this out. Okay, while the so I didn't show the best way to debug. So let me just do this now. Let me actually show proper debugging, how I would properly debug this. So we're failing on 2645, right? Sorry, I got lazy. So let's look at our code. We do top, and then we have a bottom here. And essentially we say false since we didn't switch them yet. But while top is not equal to bottom, okay, wait, sorry, let me do this. While top dot next, or where's this boolean? Oh, we're returning no. Sorry. Wow. This runs. Wrong answer. Use this test case. I'm just learning this on the fly too. 3. So we have a list of, let's just debug this properly. 2, 2, 3. What's this one? What does that even mean? 2, 1, 2. Interesting. So the test case that it's breaking on is 1. Is 2, 3, and 2. So essentially, that's a pretty crazy case. The case is like we have 2, 3, and then this is the start of one linked list node, and it kind of like points to this one. So if we start at 2 to 3, right? It's already at the end, so we move it here, move it here, and then we move it and then we move this one to the end. Sorry. So it kind of starts like this, right? So in the first move, we reach the end already. So we move this one here, and then this one moves here, right? Now in the next move, this one reaches the end. So it gets moved to the top of the other head, which is back here, while this one moves here. And then now we intersect at the middle. Wow, that's a really good edge case. Now I'm trying to think, how would I change my algorithm to support that? I'm pretty sure it's all within this change here. While top dot next or bottom dot next. Sometimes in an interview, you just have to pause and think. So what's happening is, let me think it through again. So I have one head here. Since the top dot next and bottom, so I move them forward. Oh, because I'm just moving them forward right away. I shouldn't be moving them forward right away. That's the case that's getting here. If the top dot next, I should I should first see if it even should. I should move it after. Okay, that's probably a bit better. If the top dot next is none, and move it there. Oh no, but I don't want to move it. I want to move them forward one. Should I just move them all the way till they get to the end? If top dot, okay, bottom. See, I'm flopping even this easy question. Just messing with the conditions. Well, messing around with the conditions. I feel like I'm one swap away from making it work. Really having me debugging right here. This one is a really good question. This is crazy. Okay, let's just drink some water and then actually solve this properly. I know I already said that a few times, but this time I'm being serious. So we have a few cases here. Let's just do the case where they don't actually match. Right here. Let's just screenshot this. Oh shoot. I want that question. I'm not stopping this video until this is done. No matter how long this video is, you get to see how we really debug questions. So you start with 2.6. So that's kind of what this code is doing. We started at the top and the bottom, and then we just move them up, right? But I just need to know, when do I actually stop? So move them here. Move them here. I had it close. I had it solving 37 out of 39. That's crazy. Okay, so we move them up once, and then we move them up again, right? So while I'm trying to figure out this top condition. Right, okay. We move it up 1, 1, right? Then we move this up 1, then switch it over here. Now we move it up 1, 1. Then we move it up once, once. Then we move it up once, once. So essentially, they should both go out of bounds at the same time. So while So I can kind of say while top and bottom, right? And that will pretty much run through both cases. How do you even list A, list B? Okay. So let's run that on this case. List A 264. Top that. So we'll do right this. Right. If top and what the? Okay. Let's do I should just I need to learn how to just debug it without tinkering. Like I like to tinker after I feel like it's close, but I just need to take a step back and actually solve it properly. So let's do this case. List A, list B 1 to 5. Skip A is 3. Skip A is 2. Okay, cool. Intersect value is 0. 0, 2, 6, 4, 1, 5, 3, 2. We'll delete the other test cases for now and run it. What error do we get? Oh, it worked. Okay, we solved it on that case. Now let's do the case when we have the same length. Let's do 264, 264. The intersection val should be 4. And skip 0, skip 0. How does that not work? 264, let's see. What's a skip val? Is it 3? From 0 to 2. What is skip? The number of nodes to skip ahead in list A, starting from head 1 to get to... Okay, I guess for this one, we pretty much only have to skip 2. If so, this makes them switch. So they get to the middle. So we'll say if top is not none and top equals bot, let's return top. I'm just hacking this thing. I guess once they converge, we're good. Well, top's not. Guess we just return top here. Please, 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 please. Okay. Honestly, this should be a medium question because this question is a medium question. Just saying, just saying. Please, please, please. Just say I'm right. Oh my gosh. Okay, now we just have to solve this 3 thing. This case right here is the only case we need to solve now. We're given 3 on one node. Wow, I just heard an explosion outside. Probably some fireworks. Never know in San Francisco. 3. So you're given element at 3. Then you're given an element at 2 that also points to 3. Right? So in the first pass, if 3. So the first pass, it needs to, okay, what's happening is it's like, since we're at the front, what if I move this to the back? Oh my gosh, that's it? Oh shoot. This first edge case is just crazy. If the intersection is actually the head of... So how would I solve this general case? Pretend I would do, since it's already at the end, this top dot, like moving it up here doesn't work. Moving it up there doesn't, or just moving it right away doesn't work because it gets to none. So we kind of need to, for this case, we need to move it here on the first go and then move this one here. Why didn't this work? So we can't move it right away. That's why I tried this one. If top, if top and top dot mix, I move it over there. Oh my god. Give me a second. I need to take a deep breath. I I don't know how long I've been on this, but I am not stopping till I solve this question. Give me a second. Going on mute. Taking a 2-minute water break. Be right back. Hello, hello. After this, I'm going to be, hopefully I'm not muted while this video is still running, but after this, I'm going to buy some insomnia cookies, which is this nice place in SF, because I need to take care of myself after this question. This is crazy. Okay, so we pretty much solve, like, if we add this one test case, it just pretty much breaks on this one test case. What? Which test case is that? Which test case is that breaking on top of it? Did I change something? Well, I thought we had it working. Okay. We had it working if we move it back down here, passes all the test cases. Let me just check my sound. I don't want to have this thing on mute. Let's see, output. Hello, hello. Okay, input levels is working. What I'm gonna do is, let me just check this quick. Hello, cool. Just making sure, because this video is already long. I need to solve this question. So it works for all those test cases, right? But then for some reason it breaks on this test case. So now it's saying we intersected at 3. So let's just do this. I see like a hacked move. Top equals false. Moved. There should be a more general way to do this, but because we only want to move it once per thing. The problem is just moving twice. Come on. Let's go, let's go, let's go. I'll be looking at the solution to figure out a better way to do this. But I just hacked that thing together like crazy. But it ended up working. Now, let's just look at the solution. Like, how did people do it? Oh my god. Is that really 2 pointers? Well, if... Literally 4 lines of code. What the heck? Okay, I'll be looking at that later. Let's just... So I'll be copying and pasting a bunch of this here because I said that it just generalizes. I'll say P Q, oh sorry, P Q should be solving the same problem. Instead of parent next. Instead of next, we say parent. Q, P, boom. Boom. Solve both of the questions. Let's go. Now let's just see. Now I solved both of the questions in optimal time. I mean, like optimal time complexity, but not optimal speed. I'm just trying to see what I went wrong here. Why could they do it way simpler than me? So they pretty much said while one is not equal to the other, I kind of used that same condition. Had be if PA is none, basically when it gets to the end, swap it with the other one. While PA is not equal to PB. Head if the PB is, oh my, I don't even know. Dude, okay. It's not just me thinking, contemplating how to build, like how can I improve this code? Like how I'm gonna ask GPT to simplify this code for me, and I'll post the solution because everyone's complaining how to do the most optimal solution. Let's use the top of the line model. Well, doesn't. What? So it basically shot out this solution here. Mine is slightly different. Mine still works. I feel like mine is a lot more code, but I mean, I got to it myself, so I'm happy with that. Why does this work? So the switch top and switch are honest because the pointer switching mechanism inherently ensures the traversal logic works. Instead, we directly switch pointers if they reach none. It's ahead of the other list. This is just... So once they get to the end, they switch over to the other one. So to do it, if pointer a dot next. So if it's at the end, we switch over to the other one, but the other one we move forward. But then how do they converge? I see why that works, though. There's some more math stuff that I'll figure out a different day, but yeah, that's how you solve the question. You see, I did it in a ton of code. You could do it in like 5 lines of code, but that's kind of the process that I went through the question. It wasn't optimal. I'm gonna Next time I'm gonna focus on actually running it through test cases and not just trying to on the fly make changes to it to make it work, because like that will fail you in an interview. Literally, don't do what I did here. This is how you don't do an interview. Yeah, I would have failed the interview, but we live and we learn, and I'll see y'all in the next video.